Okay, welcome to the next lecture. Our aim now is to go quickly and smoothly towards oversimplified version of quantum electrodynamics. And we will be talking towards the end of lecture today, and the one next week we will be talking about spontaneous emission and how to describe it, how to find the lifetime of the excited atom, how to find the line shape of the radiation emitted, and so on and so forth. And to set the stage for that, we need to introduce notions that probably all of you have already encountered. So I will be brief and will go quickly, just summarizing. We have to know what photons are. Instead of joking, nobody knows what photons are, but we have to. And what are these famous two-level atoms? Everyone has some kind of the intuition what it is, but I will be slightly more precise. So let's start with photons. And many of you attended my series of lectures about quantum gases last year, and others that didn't probably encountered this quantization of electromagnetic field, maybe even more than once. So I will just summarize the way I like to talk about it. I like to introduce this. And always my starting point is the general solution of free of charges and free of currents Maxwell equations in vacuum for the problem of such a field confined to a box of length L and volume V with periodic boundary conditions. It's a very convenient way of defining field. Defining field in terms of the plane wave solutions and vector, wave vector in such a box out of periodicity is always given as 2p over L times N1, N2, N3, where each of these n's is a positive or negative integer. So all these n's are 0, plus minus 1, plus minus 2, and so on. So this defines us modes of electric field and magnetic field. I will introduce a polarization vector and such a single plane wave I want to write in the form of certain amplitude of this given mode times e to minus I omega e minus k r. Of course, the electric field must be real, so I have to add conjugate if I allow for the complex amplitudes, and this multiplied by so this would be k and given polarization epsilon, yes? These are two arguments. As we know, magnetic field must be orthogonal, so it is almost the same thing, except that this is Ck. I always have to look at my notes because I hate this C in B. Why do we have this C? Because we are using legal SI units. I hate them. Okay? nodes, we know that the polarization vector must be orthogonal to K, and for every K, we have two orthogonal polarizations to really complete the basis of the solutions. So general solution, every solution of the free vacuum Maxwell equations can be written as a sum of such a beast over all possible K's, and for every K over both polarizations, and there's a lot of these constants, these amplitudes that are telling us how strong the given plane is. Now the next stage, as you remember from last year, is to look at the total energy of such a field, which, again, using these awful units, is the sum of the integral of E squared plus C squared times B squared, integrated over the whole space. Now, integration is, of course, simplified by the fact that plane waves corresponding to different K's integrate over d3r are just the volume times the delta function of k prime, and that is just a simple property of this choice of this allowed k vectors. But knowing this is not enough to really simplify everything. One has to fiddle a little bit with these polarizations to find out that actually all the terms that would have a square of this fellow or square of this fellow would cancel, and the only remaining terms are those that are coming from the product of this times this. So in fact, one can show that there is some function of k over all k's and all polarizations, 1, 2, yes, 1, 2, of these amplitudes E star 0, k I, E 0, k I. Now the next stage is to renormalize or to introduce dimensionless, if you want, amplitudes E, to figure out what should be put in out of this to make it dimensionless. And then one can rewrite this as a very convenient and nice looking sum over h bar omega k, say, times this dimensionless amplitudes kt. And I still need some index to distinguish the polarizations. And at this stage, as you all remember, close analogy to the harmonic oscillator Hamiltonian comes to mind. And as a postulate, not as a result, but as a postulate, it is very reasonable to assume that quantum theory of light should consist in replacing these fellows by creation operators and these fellows by annihilation operators. Operators that create and annihilate photons. Once we figure out, equating this with this, what are the coefficients here relating electric field amplitudes with those dimensionless amplitudes alpha, then one can write, this is this will be important with the coefficients, so I better do it correctly. One can write the total electric field vector. I better pull out my glasses so there's no mistake.
Excuse me.
Yes?
Is it a sum over polarizations or over a time?
Oh, no, over polarizations, of course. Over all case, and for each case, over the polarizations.
Okay, so this T is just...
I sometimes summation over K and over I denote by summation over lambda, so to say. So lambda would be combination of both K and I. And I will often use the notion of creation annihilation operators of the given mode.
But is this independent of T?
Well, it does not matter actually, because time dependence, as we have seen, we have seen here, is exponential.
Yeah.
So it will always cancel. So it doesn't matter whether I put it in or not.
Okay.
Yes? In other words, the expression looks exactly the same, and as it should be, it is time independent for the free field. Yes? Why should it depend on anything? Okay. So as I say, I'm beginning now carefully to write the expression for the quantized version of the electromagnetic field times sum, and I will write this lambda as abbreviation for all the now omega. Put lambda here. Now here is the polarization vector. It's the same as K and I. Yes? But I has only two values, so I will put epsilon I here. And now times A I of K or A lambda times E to I K R plus a dagger, lambda here times E to minus I K R. There is of course corresponding expression for the E field, but E field will be more important for us, so I will skip this formula for the E field. As I say, for the coming calculations, it's very important to know this coefficient and this coefficient and the way they look. Once again, they are derived from my desire to cast this expression in this suggestive form. Yes, it's not something very mysterious, it's just a very simple thing. Okay, now, as I say, by this postulate of quantization, we've got electromagnetic field quantized as a collection of infinitely many non-interacting one-dimensional oscillators. So all the properties of oscillator states, given energy state, coherent state, thermal state, all this nice operator algebra applies now to every mode of the electromagnetic field. There are several remarks that I want to make. Some of them, again, probably are a repetition of what I said last year, but I'm not sure. I don't remember all the details. First is that there is zero-point energy problem. We remember that when quantizing, looking at the quantum harmonic oscillator as a mechanical system, we had, in a natural way, 0-point energy. And, of course, we are not sure whether this perfect classical expression for the total energy of multimode field should be replaced by A dagger A, or maybe by 1/2 A dagger plus A dagger A. Of course, when these become classical commuting functions alpha, then this is just identical. Had it be this, it is almost the same as I like it, except that there would be plus 1/2 h bar omega for every mode. In other words, if I would assume that my quantization goes really exactly the way it is for a mechanical oscillator, then I would have additionally to this important operator that I'm about to use several times, I would have non-zero better, because it's infinite, non-zero energy of each mode, even in vacuum. So if I have vacuum throughout, then I should sum A over h bar omega over all the possible modes, and that is obviously an infinity. Obviously, because omega grows indefinitely. Yes? So when I add more terms, I'm adding bigger and bigger numbers, yes, values. One cheap way of getting rid of this is, hey, let's postulate that this 1/2 is not present. And then this most natural, so to say, quantization applies. In other words, let's postulate that the energy of the vacuum is 0. That's tempting, except that it contradicts experiment. And the experiment is this famous experiment on the Kazimierz force. Turns out that if you have 2 infinite slabs of metal, then even cooled to 0 temperature, these guys would attract each other. And the explanation given by this Kazimierz, no relation, is interesting. What Kazimierz did, he looked at this divergent 0-point energy, assuming this 1/2 per mode, here inside, looked at similar quantity here outside, and here outside, subtracted these two to find how the difference between these energies depends on the distance between the slabs. And this difference was still infinite. Then he divided this difference of energies by the area of our metal surfaces to get this difference of energy per unit area, still infinite. But then he differentiated this with respect to d to get the force, and that's finite. It is this force, Kazimierz force, is proportional to the inverse fourth power of the distance. It's a magic expression. And while he derived this theoretically, there was immediately an attempt to measure it. And there were conflicting papers. Some were saying, sure, fantastic. Kazimierz was right. Indeed, there is such a vacuum pressure, so to say, experienced by these things. And some others were saying, well, something is there, but there are thousands of reasons why these things are measured as non-zero. For instance, it's very difficult to get rid of any residual excess charge on these things. And of course, charges repel each other in this case, but imagine that they have different signs, they would attract each other with tremendous force compared to this Kazimierz effect, which is tiny. Yes. Some others were saying, okay, there are other reasons. Temperature is never very low, so there are temperature effects. And temperature effects mean that in this system there are some stochastic fluctuating currents all the time in these metal surfaces. Yes. And such currents, of course, create magnetic field, which then acts on little current here, again leading to some force. So in, I think, the original paper of Kazimierz appeared, I believe, in 44, some point really towards the end of the Second World War. And in the consecutive 2 or 3, maybe 5 years, the question of this force was not really fully settled. But decades later, in the 80s, 90s, people developed such a careful experimental techniques, also with the microblades, that came very close, that they measured this force very precisely, and now there's absolutely no doubt that Kazimierz was right, that his formula really works. So in other words, if we had some infinite plates somewhere and so on, then we should not perhaps forget about the zero-point energy of the vacuum field. But fortunately, in this lecture and in many other applications, we do not need to care, because this constant being finite, infinite, or whatever, would simply be completely irrelevant, would be a constant. So, of course, constant addition to the Hamiltonian never changes any dynamics. Yes. So, in some sense, it also tells you, it only tells you what is the level out of which you measure energy. And that's in, especially in non-relativistic physics, is completely irrelevant. So at this point, we simply forget about Kazimierz effect and about the zero-point energy. And the vacuum state is just defined by the condition that all the annihilation operators acting on this vacuum do vanish. So if I would like to know what is the strength of the electric field in vacuum, then I think it is obvious, it is 0, right? Because when I plug in this full, beautiful expression with infinitely many terms, there will be always A acting left and a dagger acting left, but a dagger acting left, if I put it here, it becomes A, so it is again 0. So one could think, incorrectly, that, well, there is no electric field in the vacuum. There's also no magnetic field in the vacuum. But this is oversimplified view. If I look at the E squared, then it's more complicated. Because when I square this sort of operator, then of course I get squares of annihilations that will vanish. I will get squares of these guys that will vanish. But then I will get terms of 2 kinds. In some of these cases, A dagger will be on the left and A on the right, and this will also vanish. But when I square it, there will be also terms which are what we call not normally ordered, right? There will be terms of the kind A lambda, A dagger, vacuum. Yeah? And of course, this is non-zero, because this is the same as a commutator plus same as commutator, yes, plus A dagger lambda A. This, of course, vanishes, but this is equal to 1. So there would be contribution to the mean value of a square of electric field in the vacuum. And moreover, if you really look carefully into it, it would be also divergent. So it's not true that electric field is 0 in vacuum. It's true that electric field fluctuates like crazy in vacuum, sometimes this way, sometimes that way with very high amplitudes. Yes. When people thought for the first time seriously about spontaneous emission problem, Fermi was one of the very early, Fermi's was one of the very early studies. Then there was a puzzle. We've got excited atom at some level, yes, at some energy level, and we've got photon vacuum. So how come this atom likes to go down to the lower state emitting photon? There should be some, Fermi believes, there should be some force, some action of something. Yes. And understanding of this came only after people understood that electromagnetic field should be quantized like this. And when people realized that there are these huge fluctuations in the vacuum, we often call these vacuum fluctuations of electromagnetic field. And now, the way we imagine now spontaneous emission is that even if no photons are around, there are these vacuum fluctuations which are kicking this atom, so it emits, likes to go down to the lower state and emit a real photon. Of course, this observation immediately can be generalized to any so-called Fock state. In any Fock state, in any mode, of course, for the same reason, electric field amplitude is equal to 0. Again, because here is a combination of annihilation and creation operators, annihilation with annihilator on the left and creation on the right. So, so-called Fock states, so states where well-defined number of photons is in some given mode of maybe 55 given modes. Even if n is large, is not a very good candidate for the classical counterpart of the photon field. Because in the classical electromagnetism, electric field and magnetic field both, they have very well-defined amplitudes. But, of course, you know what is my next remark. Precisely because of this classical correspondence, we have introduced coherent states. And indeed, if I take coherent state and then electric field, then, of course, A acting on the right will replace this operator by the amplitude alpha, and A dagger acting on the left will replace it by alpha star. So in other words, if I have in one mode or again perhaps in many other modes, in each of them a coherent state, then my expression for the expectation value of the electric field will be just a classical expression like the one that I started from. Yes. So coherent states are really allowing us to pass smoothly from quantum to classical description. But even this is, of course, not, even using coherent states, is, of course, not kicking out the quantum character of the field entirely, because as we remember, and we've calculated this for the oscillator, there are also uncertainties associated with the coherent state. Yes. So, this cannot be escaped. Fortunately, as you probably remember, this Poisson distribution has a width which, divided by the mean value, tends to 0 as alpha goes to infinity. It goes like 1 over square root of n. So highly occupied coherent states resemble more and more and more classical amplitudes of electromagnetic field. I could go on and tell you more about it, but I don't think it is so relevant for our purposes. The next element of the puzzle that I'm going to solve is this notion of a two-level atom. So there are many ways that one can write a Hamiltonian of an atom. One can write it in the form of multi-particle expressions with as many electrons as this atom wants to have, or the Coulomb interactions between and between each electron and the nucleus and so forth. But there is, in some sense, symbolic but simplified version of writing this thing. Instead of looking at the precise expression for the Hamiltonian, we could also think that perhaps we managed to solve the problem. So we have a set of energy levels and continuum of scattering states. And for each of these levels, these are E0, ground state, E1, and so on. For each of these levels, we know what are the wave functions, and so on and so on. So symbolically, if we manage to solve such a problem, imagine, of course, hydrogen atom was really, we know how to solve it, and the solution is known. We can write Hamiltonian in terms of its spectral decomposition. We can write it in the form of E0 times the projector on 0 state, plus E1 times the projector of 1 state, plus and so on. Plus, well, we are not interested in this right now, but plus integral from 0 to infinity over continuous spectrum. That's symbolic, but it's fine. Now, imagine that we are interested, we are really interested in this spontaneous emission problem. So we really care most, as you will see perhaps next week. It's not at all a perfect assumption, but imagine that we are interested only in two levels. Some excited level where we will put our atom in a few minutes, and some target level towards which this atom will inevitably relax, spontaneously emitting a photon. And that brings a very important toy. This toy is called the two-level atom. So the two-level atom is just full Hamiltonian of atom minus infinitely many terms, and just leaving two contributions. Contribution of the target state, perhaps typically ground state, but not necessarily, and one excited state slightly or a lot above. So this would be Hamiltonian of the atom simplified or oversimplified. Hamiltonian of the field we already discussed, and that is H bar omega lambda, A dagger lambda, A lambda. Yeah. If I wrote operators, maybe I could put operators. And then I have to decide interaction between these guys? Well, the interaction can be also simplified. And the reasonable assumption is the following. We know that the typical size of the atomic cloud, I'm not talking about Rydberg levels, I'm talking about maybe first or second excited state, is of the order of Angstrom. We also know that the typical wavelength of the spontaneously emitted light, say invisible, is what is a couple of hundred times larger. So the relevant modes of the field that will couple strongly to my two-level atom have wavelengths that is so long that I can forget about a very important aspect of my field, namely of its spatial variation. Clearly, this is not a good assumption to forget about the spatial variation if I would like to think about X-rays, but X-rays do not couple to electronic transitions. So even though they are around in vacuum, they will not be certainly, they will not be emitted while this atom undergoes spontaneous emission. Very good. So if so, in my Hamiltonian, I do not need to care about R dependence. I will simply place my origin of the coordinate system on the, well, somewhere in the atom, on the nucleus or something. And what will matter will be just the electric field at point zero, at this center, right? So, my interaction Hamiltonian in this dipole approximation will be E times R times electric field evaluated at zero, where R is the distance between, say, center of nucleus to the actual position of my electron. Yeah. So this is a dipole approximated interaction Hamiltonian. I know what to write in terms of E naught. I will take my general expression of electric field operator in terms of all the modes, and we will put this huge sum here. That is simple. But what to do with R? Well, R is of course defined in the whole Hilbert space of atomic states, but I was trying to brainwash you into believing that I can restrict my attention to this two-dimensional subspace. So in other words, out of infinitely many matrix elements of R between all possible levels, I can just extract 2 by 2 matrix, yes, which is just matrix elements between 0 and 0, 1 and 1, 0 and 1, and 1 and 0. Now, 0 R 0 is 0. 1 R 0 is 0. Why? There is no permanent dipole moment in the eigenstate of the hydrogen atom. Why? Well, because hydrogen atom Hamiltonian is invariant under reflections.
There should be R1, yes, in second time.
Yes, otherwise it would be wrong. Yes. So R is of course odd with respect to reflections, while Hamiltonian is even. If Hamiltonian is even, it means that in every eigenstate, yes, I can always choose eigenstates of my Hamiltonian in such a way that they will be either symmetric or anti-symmetric under reflection. But such a thing written in terms of integral is r times the square of the wave function. So even if wave function would be anti-symmetric, its square will be symmetric. And this is anti-symmetric, so this is 0. Good. So I even do not need 4 numbers to describe my R truncated to the 2 by 2 matrix, because diagonal elements are 0. What are diagonal elements? Well, they are, of course, 0, R, 1, and 1, R, 0. Well, they are, of course, not independent. They are complex conjugate to each other, obviously. If I multiply this by E, then it will be, we will have dimensionality of a dipole moment. And I claim that I can make it always real. Why? Well, because I always have a choice of the phase of the wave function. So even if someone gave me 2 wave functions for which this would become non-zero, would be complex, I would always fiddle a little bit with one of the phases, either of this state or that state, to make it real. In other words, with our good old friends, Pauli matrices, this thing is proportional to sigma x. Yes, d times sigma x. Or if you want, it is proportional to 0, 1, plus 1, 0. This is the very simple way of writing my 2 by 2 matrix, which represents position operator of the electron in the atom. So now I'm almost done. I'm in the position of writing my Hamiltonian. And this will be E naught projection on 0 plus E1 projection on 1 plus sum over all possible modes H bar omega lambda times A dagger lambda A lambda. This is, of course, a free field part of the Hamiltonian. And now minus. I like to pull out H bar here out of the constant that I have to introduce. Sum over all possible modes. G lambda will be coefficients or couplings. 0, 1, plus 1, 0. This is this R truncated times A dagger lambda plus A lambda for all the modes. I do not have any E to IKR because I said I'm doing dipole approximation. Yes. So K dot R is always so small that I will just put it 0 and that's it. Now, again, important thing is to remember about all the constants, and I have to use my glasses to tell you what the couplings gamma lambda are, and they are omega lambda divided by 2 epsilon 0 H bar times and scalar product of lambda. I need to cheat you a little more. Look, I can think or give an interpretation to each of the four terms that result from multiplying this sum by this sum. This is a transition that is taking us from upper level to the lower level. This is just the other way around, from the lower level to the upper level. Yes. However, this is creation of the photon and this is annihilation of the photon. So when I multiply these things, there will be two terms which are kind of funny and do not seem to correspond to any physical observable process. Namely, excitation of the atom multiplied by the creation of the photon. That would mean that the energy of the atom increased and in the same time also photon was produced. We don't seem to see such things. And similarly this times this. Yes. So it looks like a reasonable assumption to drop 2 out of these 4 terms. Because of historical reasons, that goes back to a fellow whose name was Rabi. We were talking about Rabi yesterday. It has a special name, this approximation. It's called rotating wave approximation. And it comes in various aspects in the interaction of spin with the magnetic field, for instance, and stuff like that. So we are doing one more step in simplification, and after the simplification, our interaction Hamiltonian will be still minus h bar of course, lambda, these coefficients, but now the excitation of the atom will be only related to the creation of the photon, while excitation of the atom would be only related to annihilation of the atom, of the photon. Finally, that's the final form of the Hamiltonian for which we know how to solve the dynamics. Let me start feeling with this.
Couldn't we just say that if we act with this a dagger on 0 on the left, it gives 0 because of its circumstance?
But this would be true only if we were interested in mean values. But we were interested in the evolution equation and what happens to the state. So we will be only acting to the right now. But you are of course correct that had we be interested in the mean value of some state, then these terms would drop automatically. But this is not what we want to do. We want to look at the dynamics. And quite purposely, I told you that I'm using the word cheating, because there are physical aspects of this problem that do depend on these other terms. But I will mention them when time comes. Yes. So actually these terms should be there, except that I don't like them because I don't know how to solve exactly the problem with these other terms. Okay, so my next point is to postulate the form of my state for this spontaneous emission problem. So what we want to talk about, we want to talk about initial state where atom is in the excited state and the field is in vacuum, and a whole collection of final states where atom is disexcited, or de-excited, sorry, and there is one photon of the lambda type, yes, where lambda defines both K and the polarization. What does it mean? Well, it means that I can look for the solution of the problem is a linear combination of some amplitude alpha of t times this first fellow plus summation over all possible lambdas with the amplitudes beta lambda times this 0 lambda. My Schrödinger equation with this Hamiltonian will result in a coupled, infinitely many coupled differential equation for amplitudes alpha and amplitudes beta. Obvious, yes? Again, just due to the fact that we made this rotating wave approximation, acting on this Hamiltonian, on the state, will not take us outside of this subspace, yes? That was the main reason why we did assume this rotating wave approximation, just not to couple to too many states. Even this seems to be very complicated because there are infinitely many states, yes? Well, this state we will plug into Schrödinger equation, but we should, of course, understand that there are obvious initial conditions, yes? That alpha at t equals 0 should be 1, while all amplitudes beta at 0 should be 0. That means that I'm looking at the spontaneous emission problem. That's it. Very simple. Okay. So, I gave this value of G lambda, fine. So now it is very easy to derive Schrödinger equations for these amplitudes alpha and beta. I h bar alpha dot will be equal to its energy, which is simply E1 times alpha. Yes. Part that comes from the field, of course, gives us 0, because it's a vacuum, and I've got a lambda on the right. And what happens with this? Well, with this will be minus h bar times sum over lambda, g lambda, those couplings, times beta lambda. Yes? And then there are, of course, infinitely many equations for all these amplitudes lambda. Now, what's the energy? This free non-interacting part of the Hamiltonian. What's the energy of this fellow? Well, of course, it is E0 plus h bar omega lambda times beta lambda. Yes. And the interaction energy is, of course, minus h bar g lambda times alpha. So, indeed, these guys are coupled. Fortunately, as it turns out, each beta satisfies separate equations, so to say. Betas are not coupled among themselves. That, of course, simplifies the solution. Now, there are many different ways of solving this set of equations. Corresponding, slightly different looking, but corresponding equations were solved for the first time by Wigner and Weizkopf in the very famous paper dating back to, I think, 30-something, 34 or something. But I will do it differently, not the way it is done by these old masters. I will do it differently because the way I will present can be applied to many other decaying type problems. I give you one very simple example. Imagine that we've got not some transition in the atom between two bound states, but we've got a problem of ionization. So we've got some bound state and a continuum of final states where the electron flies away to the infinity. And imagine that we are driving this or ionizing this guy by a classical monochromatic field. The way I will be showing the solution of this problem can be immediately translated into that other ionization problem, and many other problems can be handled using this technique that I'm going to show you. So it's useful. It's kind of general use, so to say. Okay, now to set the stage for that, to introduce you this method that I like, I have to remind you a few things from your math courses. I have to remind you what is a Laplace transform. It's a close cousin of the Fourier transform, except that integration is over the real axis. So if I have some function of time, yes, and I multiply it by e to z t and integrate from 0 to infinity, of course you see that if z would be imaginary, then it would be more or less the same as almost the same as Fourier transform, except from not from minus to plus infinity. Then this, by definition, is the analytic function, which is called the Laplace transform of function f of t. Now, just a mathematical remark. If what do I want? Minus. Probably I want minus here. Let me check. Yes, I want minus here. So if this is like so, this is really the definition that I want to use. If this is so, then if f of t is just reasonable, do not grow too fast, then on the z-plane, it is well-defined function if a real part of z is positive, yes? So it is very important to see that if f of t doesn't grow to infinity, even if it grows then to the right, if it grows exponentially, to the right of some line, it is well defined, it exists, yes? But if f of t is nice, actually our f of t's will tend to 0 when t goes to infinity, then this is a well-defined expression everywhere on the z-plane to the right. So to be slightly more precise mathematically, this is the definition of f of z for real z positive, but typically one can extend this definition by analytic continuation to the left of imaginary axis. It's such a simple observation. Now, again related to the inverse expression for the Fourier transform, Laplace transform can be inverted. Of course, with a different sign here. There's a factor here which is also, apart from I, which is also similar to what you remember from the Fourier transform. However, important thing, what we have here is the integration in the z-plane, which is